Hello everyone, my name is Milad Rabizadeh, and together with my teammate Kenneth Rogale, we have prepared this presentation on interactive proof systems, an exciting topic in computational complexity and theoretical computer science. In this presentation, we will guide you through the foundations, motivations, and one of the most important results in the field, which is how the class CoNP is contained in the class of interactive proofs. We begin the presentation by introducing the topic and illustrating the concept of interactive proof systems with a clear example. Then, we explore the formal definition of the model and conclude by presenting our main result, that CoNP is contained in IP. Before discussing interactive proof systems, let's define what a proof system is. In simple terms, a proof system is a formal method used to verify statements about a language. So given a formal language L, a proof system P for L includes first, axioms, which are a set of statements accepted as true without proof. And then second, rules of inference, which are logical steps that allow us to derive new valid statements from existing ones. A proof in this system is a finite sequence of steps, each justified by either being an axiom or following the rules of inference. It is important to note that a proof system may not always have a set of axioms, which means we have no prior assumptions about the validity of these statements of the language. As an example, let's consider two common static proof systems in mathematical logic. First, we have Hilbert's proof system, which consists of three axioms, as it is shown, and one inference rule, which is modus ponens. Another example of a familiar proof system is natural deduction, which is composed only of inference rules. Many consider this to be a better proof system, as it doesn't assume anything about the statements of the language. These are examples of static proof systems in the sense that a human, or sometimes a machine, starts to prove a valid statement using the system itself without any interaction. As mentioned earlier, the validity of the proof is justified by the rules of the system. Here, the only available entity is the prover. On the other hand, we have the concept of an interactive proof system, which is mainly a communication protocol between two parties. First, a prover, which is an entity with unrestricted computational power, and second, a verifier, which is a probabilistic polynomial time entity or Turing machine. Given that the prover is computationally unlimited, it can prove this statement, and the verifier tries to check the correctness of the proof by interacting with the prover. An interactive proof system differs from classical proof systems in two major ways. First, there are multiple rounds of interaction. Instead of submitting a single static proof, the prover and the verifier engage in a back-and-forth conversation. The verifier asks questions or sends challenges, and the prover responds. This allows the verifier to gather information step by step, making it much harder for a dishonest prover to cheat. Second, the verifier uses randomness to make decisions during the interaction. This means the verifier doesn't have to exhaustively check all possibilities. A valid statement will be accepted with high probability, while a false one will only pass by an extremely small probability. Now, to make the concept of an interactive proof system clear, we start with an example. So let's consider the graph isomorphism problem. Two graphs G and H are isomorphic if they are identical except for a rearrangement of their vertices. For instance, you can take the graph on the left and exchange the positions of vertices n2 and n3 without altering the edges, and you will arrive at the graph in the center. This shows that despite their shapes, the two graphs are isomorphic. This is also the case for the graph on the right. As you can see, for any two pairs of vertices, their connectivities are the same. This means all three graphs presented here are the same or isomorphic. Continuing from the graph isomorphism problem, we can encode it as the language ISO, which you can see here. ISO is in NP because the certificate is just the isomorphism function, which is simply a mapping from the vertices of G into those of H. Now, the verifier only needs to check that for every UVH in G, the corresponding vertices in H are also connected. On the other hand, ISO is an interesting problem, not only because it forms a good foundation for interactive proof systems, but also because it's one of the few known problems that is neither known to be P nor NP complete. Also, the complement of the graph isomorphism problem is not known to be NP because we don't know how to provide short certificates that graphs aren't isomorphic. Nonetheless, for any two non-isomorphic graphs G and H, a prover can convince a verifier that no isomorphism exists, as we show next.
Let's say we have a professor who has a hectic work schedule, but he's also interested in knowing whether two given graphs are isomorphic or not. Now, since he's too busy, he doesn't have the time to figure out the solution. Fortunately, he has a couple of eager, energetic grad students who have a lot of free time. So, what does he do? Of course, what any advisor would do. He asks his student to work on the problem. As is the case with any other advisor, our professor doesn't trust their answers, so he must be convinced that these students are right. Well, if the graphs are isomorphic, the only requirement is to give the mapping to the professor, and since he has a limited free time, he can verify the correctness of the isomorphism himself. On the other hand, verifying non-isomorphism takes substantially more time. Of course, the students can always come up with the correct answer if they put in the time and the effort, but sometimes they don't want to spend their whole time working on a graph problem. So they might try to deceive the professor and say, oh, hey, these two graphs are not isomorphic. Now, if that is the case, the professor cannot manually check that the answer is true, so he must get creative. While the professor secretly picks one of the input graphs, G or H, completely at random, he rearranges the vertices without the students knowing, and he sends a new graph to the students. At this point, since the students claim that the initial graphs were not isomorphic, they should easily identify the original graph, as the permuted graph is isomorphic to only one of them. If the students can reliably identify the correct graph that the professor picked, then he'll be convinced that the graphs are not isomorphic. However, if the students were trying to deceive the professor, they would have had no way of distinguishing the graphs since they are isomorphic. Now, the professor would easily know that they were lying. This interaction between a verifier and a prover is the foundation of interactive proof systems. Now that we have an understanding of what interactive proof systems are and how they work, we can begin to introduce them formally.
Now, let's proceed to the formal definitions for this idea. As mentioned earlier, an interactive proof system consists of two parts, a prover and a verifier. Let's start with the verifier. We define it as a function v with three inputs. First is the input string, for which v is tasked with deciding its membership of some language. Second is the random input, which is a randomly chosen string which empowers the verifier to exhibit probabilistic behavior based on this external input rather than internalizing this functionality. And third is the partial message history, which consists of the previous exchanges between itself and the verifier. This must be part of the input, as the verifier is only a function and therefore has no memory of its own. And the output is going to be either accept, reject, or another message to the prover where it's going to ask for another response. Next, the prover is defined similarly to the verifier, but remember that the prover has unlimited computational power. Once again, the prover is a function p with two inputs. First is the input string again, which it is tasked with deciding membership of for some language. And second is a partial message history, which consists of the previous exchanges between itself and the verifier. Again, as a function, the prover is stateless, so this context must be provided to it. And now the prover's output is simply a new message to the verifier. Now that we have the definitions of the two parts, we need to define how they interact with each other. For two strings W and R, we write this to say that there exists some valid sequence of messages of length k. And for I less than k, where I is an even number, the next message is from the verifier to the prover. And for I less than or equal to k, where I is an odd number, the next message is from the prover to the verifier. This simply means that the message sequence will always be alternating between the verifier and the prover. And finally, the last message in the sequence, message k, is accept. Now that we have defined this system, we need to define the class of IP or interactive proof problems. This class includes all languages for which there exists a polynomial time verifier, and for which an honest prover can convince the verifier of an element's membership with at least 2/3 probability. And for any string not in the language, no dishonest prover, denoted here as p tilde, can convince the verifier to accept with greater than 1/3 probability. At this point, the formal definitions of verifiers, provers, their communications, and now the class of IP problems is complete. It is easy to see that the class NP is a subset of IP. This is true because any NP problem has a certificate that can be checked in polynomial time. So the prover can provide the certificate and the verifier can justify its correctness. Also, the motivating example given earlier introduced an efficient protocol for the verification of non-isomorphism of two graphs, meaning we have shown informally that the complement of ISO is also in IP. Remember that this problem is not known to be in NP. The class of IP is surprisingly large, as we will prove next. In this section, we want to prove that the class co-NP, which is the class of all languages whose complements are in NP, is a subset of IP. In order to do this, first we will define the counting problem for the satisfiability of CNF formulas. Let numbersat be the set of strings encoding a CNF formula, phi, and a non-negative integer k, where phi has exactly k satisfying assignments. As a reminder, a language is NP hard if every problem in NP can be reduced to it in polynomial time. This is particularly important because if we can show that numbersat is a problem in co-NP hard, we will only need to verify the inclusion of numbersat in IP in order to show that co-NP is a subset of IP. We already know that sat is in NP, so its complement is co-NP. To show that the complement of sat is reducible to numbersat, we simply can take k to be 0, meaning that there are exactly 0 ways to satisfy phi, which is clearly equivalent to the complement of sat. Next, in order to prove that co-NP is a subset of IP, we will need to show that numbersat is an IP. Before we can jump into the proof, we first need to establish some notation. First, we assume that phi has m variables. Then we define phi of 0 to be phi with the first variable preset to 0, where 0 is false and 1 is true. We can then extend this notation to represent phi with its first I variables, each to be preset to either 0 or 1. And lastly, number phi is the number of satisfying assignments of phi, meaning that number phi of 0, 1 is the number of satisfying assignments of phi when x1 is set to 0 and x2 is set to 1. Using 0 for false and 1 for true, it is easy to observe that once the first I variables of phi are fixed, the number of satisfying assignments equals the sum of phi's truth values over all 2 to the m minus I ways to assign the remaining variables. This equality gives rise to two useful identities that we use later. The first one indicates that once the first I variables are fixed, the number of satisfying assignments is simply the sum of assignments that result from when the next variable is preset to 0 plus when the next variable is preset to 1. The second identity follows from the fact that once all variables are fixed, the formula has exactly one satisfying assignment if it evaluates to true, and none if it evaluates to false. So its count of satisfying assignments matches its truth value. As we know, we can enumerate all assignments of phi to count its satisfying assignments, as that would take exponential time, while the verifier is restricted to polynomial time. To solve this problem, we use a technique called arithmetization. Now, the idea is to associate each CNF formula with a polynomial p, where p mimics the Boolean behavior of phi. Since there are m variables in phi, we need our polynomial variables to range over a field with at least 2 to the n elements. For subformulas alpha and beta of phi, we apply the rules of arithmetization to convert them to their polynomial forms. One important observation regarding p that will be very important to us later on is that the degree of any of its variables is not large. The operations for conjunction and disjunction each produce a polynomial whose degrees is at most the sum of the degrees of its subformulas. Thus, the degree of any variable is at most n, the length of phi. Now let's walk through the interactive proof protocol that shows how NP is a subset of IP, specifically for proving that a Boolean formula phi is unsatisfiable. Starting from the point where the verifier V and the honest prover P are given the input phi in K, where, as we explained before, K is the number of satisfying assignments of phi. So if phi is unsatisfiable, then K should be 0. First, the prover begins by sending the value of number phi, which represents the actual number of satisfying assignments for phi. At this point, the verifier simply checks whether this matches the value K that was given in the input. If there's a mismatch, the verifier immediately rejects. Now, the prover constructs a polynomial z and sends its coefficients to the verifier. This polynomial encodes the number of satisfying assignments in a special way. The value at 0 represents the assignments where the first variable is fixed to 0, and the value at 1 represents where it's fixed to 1, and so on. The exact details aren't crucial here, but the key takeaway is that it's going to satisfy our sum check identity from earlier. So the verifier is going to evaluate number phi z at 0 and 1 and check if their sum is equal to number phi. This serves as a consistency check. So if the polynomial doesn't match this structure, the prover is likely cheating. Next, the verifier chooses a random element R1 from our field F and sends it to the prover. This random value forces the prover to commit to the structure of their polynomial across the entire domain. It makes it very hard for it to fake a convincing answer if this is the dishonest prover. Now the prover has to prove that the value of the polynomial at R1, which is number phi R1, is correct. But rather than just sending that number, the prover again constructs and sends a new polynomial, this time it's number phi R1z, and this starts the recursive step. Each time, the prover reduces the claim by one value at a time to a simpler form, again using the checksum structure. We'll see this recursion continue over the next few rounds of the protocol. Let's now continue until state M, where the prover and the verifier are working with increasingly restricted versions of the original formula. At this point, the prover sends a new polynomial z, specifically number phi r1 to rm minus 1z. This represents the polynomial where all variables up to but not including m have been fixed to a specific value chosen in previous rounds by the verifier. Only the mth variable remains symbolic as z. As before, the verifier performs a sum check where it evaluates the polynomial at 0 and 1 and checks that their sum equals the previously claimed value. If this doesn't hold, the verifier will reject immediately, once again. Then, as before, the verifier picks a new random value, r sub m, from the field and sends it to the prover. This continues the recursive reduction, narrowing down the variables one by one. At the end of this recursion, after all variables have been fixed, the verifier now checks the final claim directly. If all previous consistency checks have passed, and this final evaluation agrees, the verifier will accept, otherwise it will reject. Now suppose the prover is dishonest. In step 0, they can send a false value for number phi, but as long as it equals k, the verifier will proceed. In step 1, the dishonest prover sends a fake polynomial number phi z that differs from the correct one. Since the two distinct degree n polynomials over a field can agree at most n points, the probability that the verifier's random choice R1 fails to catch the error is at most n over the size of the field. If n is at least 10 and the field is large, this probability becomes very small, ensuring that the verifier detects the dishonesty with very high probability. As mentioned before, any polynomial p of degree at most d can have no more than d roots. Since the degree of number phi z is at most n, this means that the honest polynomial and the dishonest polynomial can agree in at most n places. And since the size of our field is greater than 2 to the n, the probability that R1 is one of the places where the two functions agree at is very small. So even if the dishonest prover passes one round's sum check by luck, that error will propagate to the next round. It will need to continue providing polynomials which agree with the true polynomial. So by the final round, the probability that the dishonest prover passes all prior checks as well as the final round is at most 1 over n. Hence, no dishonest prover can make the verifier accept with probability exceeding 1 over n. Since we showed that the satisfiability problem is in IP, we can also conclude that co-NP is a subset of IP. Using the idea of arithmetization, we can even prove that TQBF is in IP. This means that P-space is a subset of IP, which is a quite surprising result. As another surprising result, we can also prove that IP is a subset of P-space. Combining this with our previous proof, this results in the fact that IP is equivalent to P-space. These conclusions show that IP is a surprisingly powerful class of problems. And that concludes our presentation. Thank you for taking the time to watch this, and if you have any questions or comments, please feel free to reach out to us. Thank you.